Okay, this is lesson 2.1b, adding and subtracting polynomials. In the first part, we looked at what a polynomial was and how to show that polynomials were the same. Now we're going to add and subtract them. When adding polynomials, the order that you add doesn't matter. If we were to do f of x plus g of x, sorry, that wasn't a very good setup. If we're given two polynomials, f of x and g of x, if we were to add them, the order doesn't matter. If we did f of x plus g of x, we should get the same thing as doing g of x plus f of x. And the reason why is because, well, when adding even simple polynomials, order doesn't matter. 2 plus 5 is the same as 5 plus 2. They're both 7. And it's true for any type of polynomial. So let's do an example of adding. We're going to add f of x and g of x. So in function notation, it would look like this. F of x plus g of x. What's that equal? Well, I'm going to write both polynomials in brackets because anytime we replace a variable with an expression, we should do it in brackets. So start with my brackets here. F of x is 11v squared minus 6vw minus 3w squared. And this is indeed polynomial because we have terms that are products of numbers or coefficients and variables with exponents, and all the exponents are whole numbers and positive. Plus, we're going to add negative 7v squared plus vw plus 13w squared. Kind of running over into example B here, but that's okay. We got some room for example B. Now to add, simply we're dropping the brackets and collecting the like terms. Because if we have a plus sign in front of a bracket, when you distribute a positive 1 and multiply, it doesn't change anything in that bracket. So I'm going to rewrite this with the brackets open, and I'm going to be a little bit strategic here. When I open the brackets, I'm going to put the like terms next to each other. So what's a like term? Well, a like term has the exact same variable with the exact same exponents. So this might take a little bit of planning, but in the first bracket we have 11v squared, and in this second bracket we also have a term that has a v squared. So when I open it, I'm going to write it next to the other v squared term. The first bracket has a negative 6vw, and the second bracket also has a vw term, so I'm going to write it next to my 6vw. And the last term in the first bracket is negative 3w squared, and the last term in the second bracket is 13w squared. Now you don't have to do this as a first step. You can just open the brackets, keep them in the same order, and then add like terms from there, but I like to line up my like terms. Makes the math a little bit more straightforward. When you're adding like terms, all you're doing is adding or subtracting the coefficients. The variables don't change. So in my first two terms, it's a v squared term. 11 minus 7 is 4. So we end up with 4v squared. My second pair is vw's. We've got negative 6vw plus 1, so that means we're going up 1 on the number line. We got negative 5vw. And our last pair, negative 3w squared plus 13w squared. We end up with plus 10w squared. That's adding polynomials. Let's try subtracting. When subtracting polynomials, order does matter. If we're subtracting 2 and 5, 2 minus 5 is different than 5 minus 2. So subtracting even more complicated polynomials should give you different answers too. So writing the order is important. If we're subtracting g of x from f of x, that means f of x subtract g of x, because we're taking g of x away from f of x. It means we're starting with f of x, subtracting g of x. So here we go. I'm going to write it in brackets again. F of x is 11v squared minus 6vw minus 3w squared. And I'm going to subtract negative 7v squared plus vw plus 13w squared. This time the brackets are really important because when you subtract an entire polynomial, you're subtracting each of the terms in the polynomial. So I'm just going to open up the first bracket. I'm not going to change any order yet because we're going to really concentrate on that second bracket with the minus sign in front. When you're subtracting a polynomial, subtracting each of the terms, so we're subtracting negative 7v squared, which is subtracting a negative is like adding a positive, so we're adding 7v squared. We're also subtracting vw, so minus vw, and we're subtracting 13w squared. So subtracting 13w squared. Signs are really important, but the easy way to simplify this is if there's a minus sign in front of a bracket, you're adding all the opposites. So instead of negative v squared, it's positive v squared. Instead of positive vw, it's negative vw. Instead of positive 13w squared, it's negative 13w squared. Another way to think about it is you're just distributing, using the distributive property with the number -1. -1 times 7v squared is 7v squared. -1 times vw is negative vw. -1 times 13w squared is negative 13w squared. So the only difference in adding or subtracting is that second bracket, all the signs are switching. The collecting of like terms is done the same way. Now, I'm not going to rearrange this, I'm just going to strategically add the like terms. So we've got 11v squared plus 7v squared, that would be 18v squared. Negative 6vw minus a vw is negative 7vw. Negative 3w squared, negative 13w squared, negative 16w squared. Okay? We end up with two different polynomials that are not equivalent because after simplifying, they're not the same. All right, that's adding and subtracting polynomials. How can we apply this? Well, here's two examples. Taylor wants to find the perimeter of a rectangular pond. The length of the playground, it's not a pond, it's a playground. The length of the playground measures 3x minus 2 meters, and the width is 2x plus 4 meters. What's the perimeter of the playground? How do you find perimeter of a rectangle? Well, perimeter of a rectangle is length plus width plus width. So we could just add this polynomial to this polynomial to this polynomial to this polynomial again, or we can simplify and say perimeter is 2 lengths plus 2 widths. Either way is fine. Let's stick with this one because it shows a little bit of multiplication. Length is that 3x minus 2 expression, and width is the 2x plus 4 expression. How do we find the final expression? Well, we expand and collect like terms. We've got 2 of each of these terms. So we've got 2 times 3x, which is 6x, and 2 times negative 2, which is negative 4. Then we've got 2 times 2x, which is 4x, and 2 times positive 4, which is positive 8. Collect like terms. 6x and 4x is 10x. Negative 4 and positive 8 is positive 4. And now we have an expression for perimeter. 10x plus 4. We could have drawn it so you could see it too. Length and width. Length, 3x minus 2. Width, 2x plus 4. The lengths are the same, the widths are the same. In fact, if we label the other side, then it becomes really easy to see the answer. You just add the like terms. 3x plus 3x is 6, plus 2x is 8, plus 2x is 10. There's the 10x. 4 plus 4 is 8, minus 2 is 6, minus 2 is 4. There's the 4. Okay? Adding polynomials. Let's try another one that's slightly more complicated. A right cone has a radius of x plus 3 and a slant height of 2x plus 1. Determine a simplified function for the surface area of the cone where the surface area is pi RL plus pi r squared. L is the slant height. Leave your answer in terms of pi. This is going to be something new, potentially. Let's see what we got. Surface area is pi times r times L. Well, this is my radius. This is my L for slant height. So pi RL, here we go. Pi times radius times slant height. There's my pi RL plus pi r squared, x plus 3 squared. There's my expression. Let's expand and collect like terms. Here's where it gets fun. We're going to keep our answer in terms of pi. And the way we do that is we never turn it into a number. We just keep it as the pi symbol. And we distribute it and multiply it like it's a variable, because it does. It represents 3.14159. So let's FOIL and then multiply by pi. keep our pi outside. X times 2x is 2x squared. X times 1 is x. 3 times 2, or sorry, 3 times 2x is 6x, and 3 times 1 is 3. Let's get this second part going here too. X plus 3 times x plus 3. All right. In our second bracket, we're going to collect like terms. 2x squared plus 7x plus 3. And in our second bracket, I'm going to get us to the same point as we're in this bracket. So I'm going to FOIL, but I'm going to strategically FOIL and add my like terms together. And if you can save yourself this step, it's kind of valuable. X times x is x squared. X times 3 is 3x. 3 times x is 3x. So we got two 3x terms. If we put those together, we got 6x. 3 times 3 is 9. All I've done here is I've saved this collecting the like term step. And now we're at the same point in both expressions. Let's distribute the pi. For general conventions, when you distribute pi, you usually put it after the coefficient number and before the variable. So pi times 2x squared would become 2 pi x squared. Pi times 7x, 7 pi x. Pi 3 pi. Second bracket, pi times x squared, pi x squared, pi times 6x, 6 pi x, pi times 9, 9 pi. And now, to look for like terms, think of pi as part of the variable, and the adding and subtracting will become pretty easy. Ready? 2 pi x squared. There's another x squared term with the pi. 2 pi x squared and 1 pi x squared together would make 3 pi x squareds. 7 pi x, 6 pi x. Together that makes 13 pi x. 3 pi and 9 pi together makes 12 pi. And there's my simplified expression for surface area. And if you really don't like pi's in your answer, you could, this is optional step, you could common factor the pi back out. Put it in front. What would that look like? Well, it would look like pi in front, and then everything without pi in the bracket. 3x squared plus 13x plus 12. And there's your pi all by itself at the front. And what this saves you for keeping everything in terms of pi is you don't have decimals all throughout your answer, and you just have this one nice pi in front, or as a part of each of the terms. All right, that's adding and subtracting polynomials, some expanding and simplifying as well in terms of an application. Thanks for watching, and that's the end of lesson 2.1. See you next time.